On this page, we're going to look at the energy considerations for the LC oscillator, and we're going to now go back to our block oscillator as a comparison vehicle. Well, if you remember from the block oscillator, when we pulled the system to the right here to start the motion, that would be where we had our maximum stored energy. So I'm going to use 10 joules in a moment on the other side, so let's just put 10 joules in here. So let's say we start with 10 joules. In general, that 10 joules is going to be shared between kinetic and potential energy as the mass begins to go back to the x equals 0 relaxed position for the spring, where it will have maximum kinetic energy here, no potential energy. So at that point in time, the 1/2 mv squared will equal 10 joules, and we'll have 0 1/2 kx squared, and we would get 10 joules again out here when the block has reached its negative amplitude. So we have a maximum 10 joules at the beginning, kinetic energy 10 joules at the middle, and then again a maximum potential energy of 10 joules at this end, and of course it's shared in between. Since we have quadratics for each of these equations, we get quadratics for the velocity, and we get a quadratic for the stored energy. Of course, they are inverses. So this, I hope, is comfortable to you and makes sense based on what we did with our block oscillator last year. Now, let's go back and revisit and talk about the LC oscillator. Well, we know the energy stored in the capacitor, in general, I think the equation we used the most was 1/2 CV squared, but V equals Q on C, so we can make that into 1/2 Q squared on C, which is the equation we're using here. So if that is 10 joules, so we're going to use just our 10 joule example here. So if this is 10 joules, that means we have 10 joules initially stored on the capacitor before it begins to discharge at all. Now, when it discharges, of course, that energy will be stored, it will be shared with the energy stored in the inductor and the energy left stored on the capacitor. So in general, that 10 joules is stored. And look, we have quadratics. So we have quadratics again. You notice functionally they're the same. And the last thing I have on our page of notes here, it's a very short page, is the mathematics of what we did with the block oscillator, if you remember that from last year, because oftentimes test banks will inquire about the 50-50 point. So when you're at 5 joules of energy in the inductor and 5 joules of energy in the capacitor, how much charge is on the capacitor? Well, a little trick to doing that is to focus on potential energy only. So what we are going to say, we want to know the charge on the capacitor at the halfway point. So that's the Q here. So the potential energy of the capacitor in general is 1/2 Q squared on C. And now here is our trick. We're going to take 1/2 the 10 joules, but we're going to use the potential energy, Q max squared on 2. And you can see we get a lot of nice cancellation here. We lose the C's, we lose one of the 1/2s, and we are left with little q squared equals Q max squared on 2, square root, and we get our 0.707. So in terms of the halfway energy point, notice we still have 70% of the charge still on the capacitor, because our Q max is here. So again, we did this with the block oscillator, and it's often an AP test question to look at that halfway point for the block oscillator. If you recall, it was the position, right? So when you were at the 5 joule mark, where's the block? Well, the block is here at 0.707 to its maximum amplitude position. So hopefully that made sense. If you have any questions on what I've discussed on this page of notes, we certainly can talk about it in class, but I think it's pretty straightforward in terms of the comparison of what we did with the block oscillator. And we're going to move on.